Let's now have a look at the energy transported by a string. So we're going to divide the string up into a series of infinitesimally small masses. I've highlighted here the red and the blue mass. So we can imagine that there's, if you consider these as coupled oscillators, then their energy is coupled between the red and the blue. And so energy is moving along the string. Well, how fast is it moving? So waves are transport energy, and we're going to consider each point on the wave as an oscillator with mass delta m. And delta m, the infinitesimal mass, is given by the density of the string, rho times delta x. So each of these masses, the red and the blue, we can consider as rho times delta x. The energy of each infinitesimal segment is given by the energy of this harmonic oscillation. So delta E, the energy of each segment, is delta m on 2, half m, omega squared a squared. So this is the energy in a harmonic oscillation, where a is the amplitude of the oscillation, or here the amplitude of the wave, and omega is the frequency. So we can rewrite delta m as delta x times rho. Now the energy transported a distance delta x in a time delta t will give us the speed of the energy flow, so that's delta x delta t. So the power transmitted past a point in the string is delta E delta t. That's what we wish to find. We can rewrite that as delta E divided by delta x multiplied by delta x delta t, where this is now the speed of the wave. Delta E delta x we can get from this equation up here, because we can just divide both sides through by delta x. So putting that together, we get the power transmitted along the string when the wave is moving at speed c as a half rho omega squared c a squared. So here's the equation for the power transmitted. I can rearrange this in terms the rho and the c I can bring together to make a z. So here's the power transmitted as a function of the impedance. And we can use this to really explicitly treat the conservation of energy as we cross between materials of different impedance. So we derived before the amplitude ratio on reflection and the amplitude ratio on transmission. This tells you about the amplitude, the height of the waves, as you're reflected and transmitted. And it's expressed in terms of the impedances like this. But to calculate the powers, then we don't just need the amplitude, we need the amplitude squared times the frequency squared times the impedance. So for example, if we have a wave incident on this boundary through material Z1, so it's travelling to the right here, the incident power will be given by half Z1 omega squared a squared, where a is the incident amplitude. The reflected power will be given by a half Z1, because it's reflected into the same medium, half Z1 omega squared, and then the amplitude squared will be given by r squared a squared. And we can expand that to this using this equation for r. Similarly, for the transmitted power, we have a half Z2 omega squared times t squared a squared. Z2 now, because the transmitted wave is in a different material with impedance Z2. We can expand that out to this using the value for t. And I'll rearrange a little. I'll bring a factor of Z1 down here and bring the factor of Z2 up on top of this fraction like this. Now if we add the reflected and transmitted powers together, we get this, which we can take out a factor here of a half omega squared a squared Z1, and these two things, they add up to 1, as it turns out. And so the transmitted power plus the reflected power is equal to half omega squared a squared Z1, which was the incident power. One final note about calculating the amount of power transmitted across the boundary from Z1 to Z2. So the incident power coming in on Z1 and hitting this change in impedance was given by this equation here. The reflected power is the incident power multiplied by r squared, written explicitly here in terms of the impedance like this. So the ratio of reflected power to incident power is given by this ratio here in impedances, which is in fact r squared. So the amount of power reflected is given by the square of the reflection coefficient. The transmitted power is more complicated, because when we change from impedance Z1 to Z2, we don't get this neat cancellation. So here's the transmitted power. So we're in a medium now in Z2, and there's a factor here t squared. We can write that out in terms of the impedances like this. And the transmitted power divided by the incident power is equal to this. Now this is not t squared. Okay, so this is different to t squared. So while the reflected power divided by the incident power is r squared, the transmitted divided by the incident is not t squared. In fact, it is 1 minus r squared. So in order to calculate the amount of power transmitted across this boundary, actually what you do is you calculate the amount reflected, and the bit left over, that's the bit that went through.